So whenever you see something that we will identify as a cation at the front of a symbol or the front of a name, this is an immediate hint that you are talking about an ionic compound. In terms of naming them, well, let's focus on that sodium chloride again. Na and Cl. Normally, if they're neutral, we have sodium and we have chlorine. However, if you make them ions, so Na plus versus Cl minus, well, let's focus over here on the minus for a minute. Chlorine, and if you look up above, we had chloride. If you have an anion that is a single atom, so we call them monoatomic. Monoatomic anion ends in IDE. We change the suffix. We swap out the last letters for these new ones. So while a chlorine atom is the name for the neutral element, we swap out the INE for IDE. So it becomes chloride when we want it to be an anion. And this is true for any of them. If you have, let's make one more space, if I have a F, fluorine becomes F minus, which is fluoride. This is also true for things like sulfur. Sulfur, when it becomes S2 minus, if we think back to its column on the periodic table, it's 2 in from the noble gases, so it's got a -2 charge. The goes away and we become sulfide. Your oxygen becomes oxide, your nitrogen becomes nitride, your phosphorus becomes phosphide. IDE is what is used when you have a single atom anion. In terms of cations, well, we started with sodium for the pure metal, and if I want the plus, I replace Em with Em. Yes, they are identical. Technically, the cat ion, the monoatomic, so one atom cation, ends in Em. However, a lot of the things we expect to become cations already end in Em. So if you think lithium, sodium, magnesium, calcium, vanadium, strontium, rhodium, platinum, all these kind of metals that end in Em. Remember I said sodium, lithium, potassium, the things in the far left column and even far two left columns, you don't find them on Earth in any form except already charged. So when we first found them, they were charged plus, and so we named them like they were charged, and we never had the pure metal, so we never had a name for when they weren't charged. By the time we figured out how to make them, everyone just called them sodium or potassium, and so it was decided rather than make up a new name, we just called them sodium metal to tell people that, oh, it wasn't a sodium ion, it was the neutral form. And that is still true this day. So while Em is the technical ending for cations, it won't really make much of a difference for most of what we do. Let's go back, talk about these anions that do get the difference. So if I have something like sodium sulfide, if you pick up a bottle and this is on it, well, we can identify from the first part. Sodium tells me that I definitely must have Na plus around. and sulfide, well, that's an anion, it's telling me that, well, IDE tells me it's a monoatomic, so it's one atom, and the sulf tells me it's a sulfur. So I put in the S, I go figure out from the periodic table what the charge is, it's 2 minus. So I know that this compound is made from sodium ions and sulfide ions. But in this case, what I'll find is that I actually have to have 2 sodiums for every sulfide. And the reason is your molecular formula must always be neutral. So must have no charge. The idea is if you ever paired just 1 sodium and 1 sulfide, you would still have a leftover negative, which means any other positive thing that ever came along would stick to it. So you had to have 2 sodiums per sulfur for it to be balanced out and stop attracting new things. This is true for all ionic compounds. If we do, well, we have fluoride up here, so let's do a sodium fluoride. Well, we'd look at the name, we'd say, hey, I have a sodium cation. Fluoride is fluorine with an anion, which is F minus. So if I have 1 sodium and 1 fluorine, I'll balance my charges. So all I need for sodium fluoride is 1 of each. And so NaF is sodium fluoride, where Na2S is sodium sulfide. You'll notice that the names don't tell you how many of each ion. Whether it's 2 sodiums or 1, we say sodium and nothing else. We are left to do the math. This is why recognizing what the charges that the different columns in the periodic table tell us, by knowing what they are supposed to be, it helps us determine these formulas.